All right. Good morning, everyone, and welcome to this series of workshops in Paradox. I hope you all know the topic of today. It's Introduction to Signal Chain Hardware for 5G base stations. Okay, and let me just introduce you to the speaker of today's workshop. Please meet Mr. Jagannathan Venkataraman, who is Principal Architect, Analog Signal Chain Department in Texas Instruments. Mr. Jagannathan Venkataraman is a principal architect and distinguished member of technical staff with the Analog Signal Chain Department at Texas Instruments, Bangalore. He received his BTech degree in electrical engineering from BITS Pilani in 2002. His research interests are in cutting-edge signal chain architectures with focus on high performance, high speed, and low power designs for wireless communications, wireless data interfaces, clinical biosensing, 3D time of flight, and camera imaging systems. He has developed highly integrated, high performance, and low power mixed signal SoC products, including 4G and 5G trans receivers, Ethernet, retimers, medical front ends for different end systems, and he holds 40 plus patents granted by US Patent Office. So please welcome, sir.
Thank you.
So please, whenever you are ready.
Yeah, I can start. So good morning. Before starting, right, the presentation, right, is about signal chain hardware for 5G base stations. But considering the background and the diversity of people who are attending, right, I try to make this presentation more sort of intuitive, not going into too much theory, so that you are able to grasp, and at the end of the presentation is like you get an overview of what a signal chain means and some of the basic concepts of communication I am trying to introduce before we jump on to the signal chain, just to see how the signal chain goes into, right. I am not going into too much of mathematics or calculations or something. It is more intuitive. We try to at the end of the presentation you should just get a feel of what it takes in a base station or a signal chain, right. What are all the different blocks, what are the key parameters, and then at a level that you can map it to at an intuitive level, right. That would be the goal or the objective of the presentation, not going into too much of details where a lot of background and assumptions are to be made, right. So I try to make it as simple and intuitive, and then maybe at the end of the presentation, if you still have questions, right, we can go details of some of the things that we want to elaborate. So yeah, so this, I think this picture, right, all of you would have been familiar, like you would have seen this in most of your apartment tops or ceilings, and clearly you can indicate this is a base station. So this is how the base station or a cellular tower, right, that appears in most of the places in India right now. But if you see the remaining things, right, if you see the second picture, I think you can't make out anything from here. It's just a lamp post, but actually, right, this is also a base station. I'll come to what this is. And the third part is, you can see the third picture, you can see some router kind of thing sitting. So obviously we are all used to the Wi-Fi routers, but similarly, right, as 5G or the newer technology evolves, right, these are also called small or pico base stations. So these also act like a base station. And on the right is actually a 5G base station or a 5G tower. So you can clearly make out a difference that going from the first part to this, right, the look of it is also completely different. And as we go through the presentation, right, we'll see what is there inside this box on the right side, and what are all the different blocks and what are the things that get to it. Okay. So just to elaborate, right, so this is the 4G or the 3G, 4G, all the base stations look similar on the left side, and the lamp tower that I was talking to is called a small cell. So it's also a mini base station, but it covers a smaller area compared to a bigger tower. And Wi-Fi we are all familiar with, but in addition to Wi-Fi, right, there are something called distributed antenna systems. So the way the technology is evolving, right, you already had a single tower that supported mobile communication, but with increasing bandwidths and the density of users increasing, let's say if you're in a stadium or you're in a mall, right, there are so many people who need to use the internet or the bandwidth, right. So you can't just rely on a tower which is sitting somewhere else. So the way things work is you have a distributed antenna system where the cell tower talks to some of these hubs that which is shown on the top, right? These are the mini base stations that sit in your mall or maybe even take your institute, right? You can have few of these in your bigger corridors or verandas, and then from there you talk to your mobile user or a cell phone. And this 5G base station will come to what this involves. This is like a replacement of the tower that you see on the first picture. Okay, so this slide just tells you the brief evolution of cellular communication, right? As we go from say 90s or 80s to all the way till the current generation 2020. So the G stands for different generations. So 1G, 2G, 3G, 4G, 5G, and there's already talk of things going to 6G. So fundamentally, if you see, right, the use case that it supported and the bandwidth. Clearly, if you see the graph of the curve, right, there are two important parameters that you can see that is driving this evolution. One is when in 1990s, right, the cell phone or voice calling was a predominant use case for cellular communication. So bandwidths were very small because we know voice, you just need the bandwidth to transmit voice is very less. So then slowly things evolved. You started to have text, so you needed more bandwidth. Then you started to have as a 3G evolved, right? You started using internet within the phones, so you needed more bandwidth. So you can see on the top numbers, right, these are all bandwidths. We'll see what this means eventually, right? What this translates to, because we are all familiar with Mbps, kbps, because we are used to our broadband speeds or mobile speeds when we use our download or upload speeds, right? We'll see what it actually relates to in a cellular base station or a signal chain. So as you go, right, 4G, which we are currently in, and the cusp of transition from 4G to 5G. So you can see already we are supposed to hit close to 1 Gbps theoretical, meaning it says 1 Gbps theoretical, but the actual use case could be very different according to the user or the density. But you can see clearly the spectrum of applications that is enabling is much larger. So even 4G, right, you can do a lot of things like Internet of Things, where you can connect multiple things to your Wi-Fi. And even in 4G, right, you would have seen, if people have viewed, right, you also see a voice over LTE where you could use, when you're trying to call someone, it's not just you use your mobile tower, Wi-Fi also gets connected. So you can actually, part of your Wi-Fi bandwidth is also used to pass on voice through the network to the other place. So as you evolve to 5G, the rates are going much higher, like 1 Gbps to 10 Gbps is a theoretical rate, and then there's more networking of things that are going to happen, in the sense like you can do a lot of things, like you can do remote, like AI is AI and machine learning, right? They all rely on, actually you have many modules where there's you don't restrict a network to be just sending information from one place to another, but you're just connecting all the modules that are available as a cloud, so that you can get information or have remote video conferencing or whatever you want, right, remote. But you need a lot of bandwidth for it, because back and forth you have to interact with so many things, right? So that's what 5G is actually enabling. And 6G, there is still I think thoughts, already 6G is starting, maybe it will materialize in 2030, 35 or whatever, maybe 8-10 years from now. And still here, right, there's further more being thought through, like the bandwidth will further increase. We don't know what it is, but maybe it will go another 5 to 10x more bandwidth, and it will enable a lot of things like machine automation, robotics and other things which you could control using your phone. So that's where the things are evolving. Okay, so let's now step back and then start with some basics, right? So what just any communication system, right, is a generic system. You have a sender or whatever, you have a data or some information you want to send, and there is a recipient on the other side, right? So what are the basic things that you need to do? The data that the sender wants to send has to be transmitted, and there is a medium over which you transmit. So earlier, if you use fixed landlines, right, the medium of transport used to be a whatever, like a cable or a fiber or whatever, a cable line or a DSL line, which used to be the transmission path. And then on the other end you need a receiver which detects this signal and then decodes the information and sends it to the recipient. This is the basic signal chain, and the transmission path or the channel, right, is laden with a lot of unwanted things like noise. You can have bends in your cable. There are some multiple things that can happen in the cable depending on what the channel is. So the same thing, right, in a wireless simulation, the basic signal chain is the same from a top perspective. It's just that we will introduce what these concepts are. It's just that the medium of transport is free space or air, right? So it's wireless, so you don't have any wire running from transmitter to receiver, and that's a free space that you want to send information with. So it's the same concept, like say take the data, somehow you'll have to have a transmitter that sends the data through air, and on the receiver side, right, somebody has to plug the information from the free space and then transmit and decode that information to recipient. And that's the basic difference between a wireless and a generic system. The medium of channel is different. We'll see what these mean as we move, right, modulation, demodulation, why it is required, why it's different from a wired communication. Okay. Okay, so let's start with like slowly build up what is the end objective of any communication system. Like any communication system that people build, right, what are the key things they try to achieve, right? So one is the important thing is you want to receive the maximum amount of information from one place to another in the shortest time possible. That's the basic motive, right? So speeds, right, like even when we look at a broadband connection, if you want to just buy a broadband connection, we look for we compare different vendors, we see who gives us the best speed. So why do we need it? Because the amount of data that can be transmitted in a shortest time, right, that's what the Mbps or the Gbps means, like megabits per second or gigabits per second, right? So what does it enable? It enables like fast transmission of data, and it also means that you can get, if you want to download something, right, you don't see the nagging that hourglass or something circulating, so you don't want to get all this. So the speed is very critical in any communication system. So the key aspects, right, we'll come back to what this means, right, in an actual hardware chain, right, what it translates to is bandwidth. We'll see what bandwidth is, and what is latency. So latency in simple terms, right, if you want to play a game, for example, through your net to a different person, right, it's not just one way of communication that is coming. You're not just downloading something, you're just not uploading something. It's an interactive thing where you send something, the other recipient receives the information and he sends it back, like he's responding to it, right? So if there is a lag in it, right, then you will feel that like you are doing faster communication and you don't get the reply back or acknowledgement back. So that's where latency is like the amount of delay it takes for the information to go back to one place and come back, go and come back, like a round trip delay, right, is latency. So obviously latency has to be very low for an user experience to do any of these, whatever we discussed in the previous slide, like 5G or 6G, right, where we are saying we are going to do surgery remotely from one place where a robotic arm is sitting in some other hospital and the doctor is trying to control. So he needs real-time feedback from the remote location, wherever it is. So latency is one of the biggest care abouts that will come in. Okay, so what is the other thing like that is important is it has to support multiple users. So when we saw the previous slide, right, where if it's a wired communication, you just have a single wire, right, and if many users have to be connected, you have multiple wires. So the hardware is for every user, end to whatever, sender to transmitter, sender to receiver. But in a wireless space, as we said, right, the channel is space or free space or air, right? But you will have so many people, so the channel has to support so many users simultaneously. So you can't, there's no channel, right? There's not like a fixed channel where you can say, okay, I'll put a wire from place A to place B and he communicates and place B to place C, because that will not work when you want to do Internet of Things. So it has to be a centralized system where multiple users have to talk within the same medium. So how do you do that? Like, let's say, right, if you have in a classroom, right, there are 10 people and each one is talking to some other person and then very loudly, right, it's very difficult to figure out, there will be noise. So there is something that we will have to do to make sure it's the same thing that happens in wireless space. If there are millions of users or in a local area, right? Let's say we are about 30-40 people here, and we are having a mobile phone talking to someone, and then the free space is clouded with a lot of information, but you try to get only the information that you are talking to. You are not taking the crosstalk from other person, right? How that is to be done, right, is all what decides other aspects of a communication system. So what we call spectral reuse is basically spectrum. Spectrum is basically free space or air. How do you reuse the same spectrum for multiple uses? So that is something that is very important if you want to build a communication system or any standard. The other thing is multiple access, similar to like many people have to have access to the system, and you can't have a time down. Like say, okay, when somebody is talking, right, you can't say other people have to be quiet. So you need like everybody has to talk through simultaneously or have access to the communication system simultaneously. And as I mentioned, right, you have to share the same channel because it's free space. So there is something called interference, like the example I gave, right? If there are 10 people talking loudly, right, you will have to figure out, even when we talk in a classroom, right, it's very difficult to figure out, and we ask people to shut down. But how do you avoid that in a real communication system where you pick only the information that you want and reject all the other information? So some of the key aspects that these are all the jargons that I'm trying to introduce. We'll go through some of these as we go through the presentation, so it will become clear at an intuitive level. So something called modulation, which we saw in the previous one. Why that is important, right? That is because of supporting these multiple users. We'll see what that means. And that is called blocker tolerance. I think the way to give a example to this, right, is similar to this. Like let's say if two people are talking and one guy is talking very loud, and there are two other people who are in the same room who are trying to listen. The tolerance of that person, right, the person who is receiving, how feeble he is able to receive the information that he wants in the presence of some other guy's communication, which is very strong, right? That is like a tolerance. So the blocker is basically unwanted information, and how you are tolerant, right? How feeble information or how high unwanted signal you can actually detect your information, right? It's called blocker tolerance. We'll see. Meaning I'm just giving analogies. And then there is something called emission. So emission is basically, we'll come back to, meaning at a later point, and interference to others. Like suppose one part is I told you about tolerance, right? So the ability of a person to detect in the presence of noise of some other guy talking. But once you have a communication system, right, you can put in certain rules saying like the person who's talking, he cannot be too loud, meaning his volume or decibel level has to be controlled. That's where this emission and interference comes in. So when a communication system is designed, they have some specs of, okay, if somebody is communicating in a channel, he should not send some other information in a different channel, or there should be some level of power level, right? You can't just blast information so that the other person cannot receive it. And a simple example is you would have I think encountered jammers, right? People would have, what is a jammer? Actually, jammer is nothing but it's a device. When you have a mobile phone, you just stick into it, right? What is it doing? It is just blasting some information in your mobile phone frequency range, so that your entire receiver, right, is not able to receive your wanted information. It just blocks, or it just overloads your receiver with that. So that's all. Jammer, once you do it, right, you're not able to communicate to anybody. Is because they're actually breaking this blocker tolerance rule by putting a jammer, so that none of the devices are able to detect information, and then it gets completely blocked. Okay, so the other part is like, because we have seen the first picture, right, where you see pictures of antennas or radio towers, right? Obviously, you don't want something to look very big, like a huge antenna sitting on your building or an apartment. And if you see the like a Wi-Fi router is very small, because it's a small range router, right? Similarly, if you see on the right side, the picture that we saw, like a 5G base station. So obviously there is more push to have smaller and smaller equipment size. You can't have a large equipment. We'll see what it means. What does that translate to in a communication system? So actually, just to give examples, right? If you see, I think maybe even in India, you can see that, right? Nowadays, right, if you see 5G base stations, right, you can't actually make sure, or you cannot make that it's a base station when you're traveling. So it'll be like a tree or a lamp post, right? Something will be just sitting. It'll be camouflaged into a lamp post or something. But how are they able to do? Because the equipment size or the antenna size or the equipment is so small, they're able to put into a structure. But if you see the traditional FM or AM towers where the All India Radio used to transmit, right? You can see like big towers with that huge antennas. So we'll see what it means. So something called a carrier frequency, right? Or the antenna size is dependent on the carrier frequency. We'll see what it translates to as we go further. Okay. And then the other part is to send and receive to long distances as possible. So this is one of the key aspects of any communication system, right? So you want to send, right, to a very long place, because you're not communicating to someone who's very nearby. You want to communicate to as far as possible. So obviously, how do you want to do the in a communication system perspective? There is a transmitter. You have to send power, and you have all these base station towers. Obviously, the objective of any vendor, like whatever they are, say once they put a base station, right, or a tower, the tower forms the hub where all the mobile users talk to, and then the tower communicates to the next tower, and that's how your information jumps from one place to other, right? So they don't want to install too many towers, because obviously there is cost, maintenance, real estate space. So they want to reduce the amount of towers and then cover a large area within one tower. So what does it involve? So it involves how much power you can blast, and then even the mobile phones that are receiving, right, can they receive small amount of information? If they can detect the message or your data within a small amount of power, that's important, because it reduces the number of towers that you need in a particular area, right? That's going to save cost. So that is where something called transmitter power, sensitivity, will define what sensitivity is later, and SNR. I think SNR is signal to noise ratio. It means like, see, obviously it's very easily said done, right? When you talk, right, it's just you want to detect that information, but there's always noise. Like whenever we are in a closed room, right, we are much better, but you are in a road, right, you are just talking, same set of 5 people are talking, but you will have cars going in, then some construction work happening. These are all unwanted information, there's noise. Same thing when you send some information in free space, there's a lot of noise, and the noise, right, is an inherent part of any real system. It's like nothing is ideal in the world. Like in a communication system, right, if you put any circuit, right, in any circuit or something, there is always like temperature dependent, what we call as thermal noise. Like there are free electrons in any semiconductor, but or you take a simple resistor, right, you take a simple resistor, you would all be very familiar. You don't apply anything, you just put it to a your spectrum analyzer or something, right? Ideally you should not see anything, because it's a passive resistor, you're not given anything, but you will always see something moving in your scope. It's because once you set something, right, there are always free electrons that are moving, which is dependent on temperature. So that noise, right, will always be there. So you have to detect the information in the presence of noise. So that's what signal to noise ratio means, is how much of signal you can detect in the presence of noise is called signal to noise ratio. So we'll introduce some of these, and then you will understand better as we move on. Okay. So before that, right, as I have introduced the objectives of the communication systems and some of the key concepts, right, we will just go through some of these key concepts to understand what they are at an intuitive level, and then we'll see how, right, when you go into a signal chain hardware, right, how some of these are actually deciding the blocks that are coming into a signal chain. Okay, first let's start with what is bandwidth, right? So bandwidth that we all, at least generally people know, is our download bandwidth or upload bandwidth. What we say is Mbps, Gbps, right? What does it relate to? Like eventually in an actual communication system, or like you want to build a hardware, right? What does it translate to? Okay, so in a crude sense, right, what bandwidth means is, if you have any signal, right, I don't know whether you will all be familiar with a time domain. If you have a signal, right, there is a time domain response for the signal, and you always can represent the frequency content of that signal in a frequency domain. I think we're all theory of Laplace transforms and other things. I think you would have probably, many of you would have got introduced. So it's basically, right, if anything is there, you can look at it in a time perspective, but you can also look at it what is the frequency content of that signal. So whenever you say bandwidth, right, it is the max minus minimum frequency content of any signal, right, is called bandwidth of the signal. We'll see what it means. So let's say these are the two signals, right? Let's say somebody is like, we'll take, right, this is like somebody is speaking or somebody is playing music, right? Different octaves, right? They're playing different musics, like let's say a keyboard and you have a violin or a guitar, right? You play, and somehow you're translating that to through a mic, and then I've plotted this information, right? You see what the mic output, right, is what is shown. So depending on, right, you have a soft tone, lower instrument, or you have a very tonal high frequency instrument like a guitar or something, right? You will see, you can hear the differences, right? What it translates to. So one signal, right, could be moving very fast like this, or if somebody is talking, right, let's say somebody is singing very slowly, or somebody is just making a jarring sound up and down. So the way you look at it, right, there is something that is changing very fast in time. Like if you look at some signal, that is the top one that it shows. On the bottom, right, there is some parameter, either it is voltage or current or whatever you take, sound level or whatever, right, it's changing at from a time base, the x, right, it's changing slowly. You can clearly see the top one, right, has a lot of excursions within a short time, whereas this is moving slowly in any sense, right? So what does this mean? This is a time domain, right? It's an equivalent, right? You can have a frequency domain. So that's what I was meaning. Like if somehow, right, I try to find out the frequency content of this two signals. So what it means that obviously Fourier is one of the, I think the Fourier series Laplace transform, right, is one of the key innovations or whatever, like key discovery in communication system, right, where it gives you an idea of how to map, because if you look at these two signals, it's very difficult to visualize what it is. Whereas if some of the things you look at frequency domain, right, what is the frequency content? So this is just saying what is the amount of frequency content in the signal. You can clearly see the top one, right, will have the FL and FH are basically two numbers that I've put in frequency axis. So you can see, right, this has a larger spread of information compared to this. This has a lower spread of information. So when you say bandwidth, bandwidth is basically the difference between the highest frequency and the lowest frequency you can get in a signal. It's like the difference of it, whatever the bandwidth, right? It's like a band. If you do it in frequency, it's like a band. The width of the band is actually what is bandwidth in actual sense. And all the things that we know of GBPS, MBPS are all related to our upload download speeds or whatever, but in a real system, bandwidth means what is the maximum minus minimum frequency content of the signal. This is called bandwidth. That's how it is called, the band and the width of the band. So you can clearly see this is high bandwidth, we call wide band, and the lower one is narrow band. Because these terms I'm just introducing because as we move on, right, there is something we will encounter these terms as wide band and narrow band. So we'll see what these mean. Okay. Okay. So now, right, you can clearly see what it means. If you have a 1 Mbps download speed, it is 1 megabits per second, right? 1 Gbps is 1000 megabits per second, right? 1 giga is 1000 megahertz. So you can directly translate what this means. You can just map it to the top. Like 1 megabits is like in a second, right, I'm actually transmitting 1 megabits. In the other case, I'm transmitting 1000 megabits. Clearly you can see the 1 megabits, right, will be like the bottom curve, and 1000 megabits will look like the top curve, because you're just sending so many per second, right? Per second is within a second how much faster you're sending. So clearly you can directly map it, right? The 1 megabits per second will translate to a lower bandwidth, and 1000 megabits per second or 1 Gbps will translate to a larger bandwidth. So eventually, right, the bits per second of data rate translates to a higher bandwidth of the signal that you have to occupy, which it needs, right? So that is what is the summary of this. So clearly, as you want to push higher and higher data rates, like we saw, right, 1G, 2G, 3G, 4G, 5G, where it's going from voice to messaging to video to we saw till say 10 Gbps or 100 Gbps, right, as we move on to 5G, 6G. So what it involves like larger and larger bandwidth. So when you say bandwidth, now you just look at it, we'll see the details later, but it just means like the free space, right, what you need for transmitting that information, you need larger bandwidth. So you would have all, now you can relate to what this spectrum auction, right? I think spectrum auction happens in even India for 4G, 5G, and there are a lot of controversies around it as well. But clearly now you can relate to, right, what it means. Like if somebody is buying a spectrum, he's actually buying how much of bandwidth he wants. Like he's just buying, saying, okay, the free space is there, and that is auction saying, like if some Airtel brings it, right, Airtel buys, right, they buy say 50 megahertz, this FH minus FL is equivalent to 50 megahertz, and somebody else will buy 100 megahertz, somebody else will buy a 20 megahertz. So that is where the spectrum and the bandwidth is getting related to. So if somebody wants to run a 4G or 5G area, obviously they need higher and higher bandwidths, because as you see, right, higher data rates you want to support, you have to buy a larger bandwidth to support, to send the information. Okay. Now we'll see what is modulation, right. So we all saw, like you have some information that I have to send. Let's say it's a voice or a music or something, right. We all know, like voice, if you take a normal person's voice signal and convert to the same thing, like you take a mic and then you put it through a spectrum analyzer. Spectrum analyzer is basically an instrument which does time domain to frequency domain transformation of any signal you give, and it plots what is the frequency content. Usually voice is within, say, 10 kilohertz, 20 kilohertz. I think the maximum frequency of voice is 20 kilohertz. So that's the only information. So if I have to send the 20 kilohertz to somebody, right, I have to speak on a phone, so I have to send the 20 kilohertz, right. So one thing is you directly send that information through air or through wire, right, that is what. But what is it needed? So modulation, right, is a process of superimposing message onto a carrier signal. So we'll see why that is needed. See, one is, like I said, right, you speak like how we speak here, right, the voice just goes from free space from one person to other, but you can't do this over long distances because of the reasons that we will see. So you need something called a modulation, where the message that you have to send, right, has to be put into a carrier packet, and you have to send the carrier to a different person, and the other person will open the carrier, or the carrier sends the information, then he decodes the information. So analogy is like this, right. So the message is in that whatever he wants to transmit in this hand, a paper or a message. You can't just put the message, you just throw the message, right, it will not go to long distances for whatever reason, right, it's just a paper or something. So somebody has to take that message, who is a carrier, and put it into a place of where the recipient is. So modulation is process of actually superimposing a message onto a carrier, and usually this carrier signal is high frequency. We will see why that is needed as we go on, and that is what a modulation is. Modulation is actually somehow, right, you have to convert the message signal and put that information onto a different carrier signal. That is what is modulation. Okay, so this is what we saw. So now I'll connect to what the size of the equipment that we saw later, right. So obviously if any signal is there, you have a wavelength. They're all waves, right. When you talk or when you send a mobile communication or something, they're all radio frequency waves, or it's all just a wave information. So wave has a particular wavelength, right. So the larger the frequency, smaller the wavelength. So frequency and wavelength are inversely proportional. So if you have a wave which is very small in frequency, the wavelength is very large, and it's a vice versa, like if you have, right. So one thing, right, I'm not going to the details of it. One thing that is in an electromagnet theory or antenna theory is the size of the antenna, right, actually is proportional to the wavelength of the frequency that the antenna is trying to emit or receive, right. So that's where it comes in. So if you say, right, I have a 1 megahertz signal, right. Let's say I generate a 1 megahertz signal, and what is the wavelength of it, right. So wavelength is speed of light divided by lambda. That is a wavelength, right. It's inversely proportional. You can just say wavelength, I said, right, the higher the frequency, lower the wavelength. So same concept applies. So 1 megahertz, right, translates to 300 meters. So typically the antenna size for somebody to emit information at that frequency, you need to provide an antenna which is somewhere in this order by 2, like wavelength by 2 or 4, I mean that depends, but it is in that order, proportionality order. So you can see 300 meters. So if you take a by 2, right, 150 meter antenna has to be placed to send information across whatever towers we saw there. So that's going to be very huge. You can't keep that for you can't have that big an antenna and then replicate it everywhere, right. So that's going to be a problem. So now correspondingly what you do, you somehow, right, I have a higher frequency, I know my antenna size or wavelength is going to come down, my antenna size is also going to come down. So this is where the concept of carrier frequency comes in. Why do you need to modulate? The modulate is because I said my voice signal rate is only this much, 20 kilohertz, because whatever I do, right, I can't exceed that. The human voice cannot exceed 20 kilohertz, or even music, right? Maybe it will go to 50 kilohertz or 100 kilohertz, but you can't go more than 20 kilohertz when somebody talks or shouts. And I can't use an antenna to transmit it and somebody receives it, right? So now the carrier thing comes. Now I know, okay, if I choose a different carrier frequency or a higher signal, somehow I put this information onto it, and that to transmit that information, right, I need a smaller size. That's where modulation comes in. And why that is required? Because we said the objective of communication system is to have lower size equipment, right? You can't have a very large equipment. So that's where what modulation comes in. So the other part is like one other aspect of what is the objective we saw is like multiple user access, right? Like I said, you have one free space or a channel and many of them have to talk, right? That is one. Like you, for example, right, Airtel is there, Jio is there, whatever, Vodafone or Idea is there, right? So everybody has to talk. On top of it, you have Wi-Fi in your homes, which also has 2.4 gigahertz or something. Then you will have Bluetooth. So there are so many things, right, which are all relying on the same channel. But how do I now differentiate the information that Bluetooth information only connects to it, and then you don't pick that information because everything is free space, right? So what do you do? So that is where again a modulation comes in, because now I said whatever information you want to put, you can actually, if you are able to put it into a carrier, now each of these systems, right, will use a different carrier. For example, Wi-Fi will use a different carrier frequency or a signal where it embeds the information. Your Airtel will use a different information, Jio might use a different information, satellite phones will use a different information, Wi-Fi will use a different information. So how do you do it? It's the same information, but I have allowed to pack it into different frequencies so that the Bluetooth guy knows my carrier frequency is only this. So he will look at only that packet, and from there he will try to open up his information. And your Airtel guy will look at a different frequency and he'll open. Then that all of them can exist in free space, and then you can pick and choose. For that, right, you need to space out the information into different packets. That's where one of the other important use cases of what modulation is, right? That's what I have written on the bottom, right? FM, everything has to, and then you have your defense systems, satellite phones, everything is all coexisting. So what do? They have an entire spectrum, which is your free space is like it's free in that sense, right? That's where it comes. They allocate. They're saying, okay, the satellite phones have to use a particular carrier frequency or band of information, and all our commercial communication systems have to use something. 3G has to use something, Wi-Fi has to use something, because you would have seen, right, many of places where even your homes you have a modem and you have your Bluetooth. Like many times, right, you will get a interference if you have a Wi-Fi router very close to your Bluetooth where you're receiving, right, you'll always throw up something saying, okay, there could be possibility of interference, you switch to a different channel or something. You will always get these images. It's basically because of this. You have an interferer from one carrier frequency to the other, right? Unless they are spaced apart, right, you will always have interference between them. Okay, so now we'll go into what are the different types of modulation. When I said that modulation is, we said we have to superimpose an image, right? So let's take simple example, right? So this is very like if you see, right, any in a signal processing theory, right, any information, right, that is the beauty of Fourier series or whatever, right, any information or any signal, you can break it down into a simple sinusoid. You know, sine and cos waveforms, right, like a sine theta, cos theta as a function of time. Anything can be broken down into linear combination of cosines and sines. So that is any information, any time, whatever I drew, all that information, anything can be broken into that. So if you do an analysis, you understand the concept in a sine wave, same thing applies to any complicated signal, because any complicated signal is some combination of sinusoids and cosines and sines. So you can always break it, and you understand this concept, right? Everything can be extrapolated to any complicated system. So assume this is your voice signal, right? I'm just taking it as a sine. Somebody is just singing in a particular tone, there's one information, and this is what we said is a carrier signal that we want to put for antenna size, let's say, right? This is a very high frequency. It shows that it's moving faster, so it's high frequency. This is moving slower in time. So somehow, right, I have to, this is the information that I want to send, and this is my carrier. Somehow, right, I have to send this information packed into this. what do I do? There are three, we'll see, right? There are broadly three different ways of doing it, right? So we'll see, one is called amplitude modulation. So you can clearly see, this, the left side is a slow moving signal and this is a fast signal. When you say amplitude modulation, what I do, right? Just I'll say, let's say I multiply these two. Somehow I figure out a block that does multiplication of this and this. Basically, it just changes this guy's amplitude, meaning the carrier signal's amplitude or the level based on this. So that's what is this. If you see, right, you can clearly see this was your high, but then I had superimposed this information on top of it, right? So what this actually means, right, is amplitude modulation, because if your carrier signal was just high frequency, we saw that waveform. Now there is some information riding in the amplitude, which is actually denoting your message signal that you want to send. This is all meaning mathematics. If you see, effectively when you multiply those two signals, right, I said there is one sinusoid, there is another sinusoid, both were sinusoids. You just multiply whether it is cos or sine. Fc is basically frequency of this high carrier signal, and Fm is the message signal. Clearly you can see, right, this is the time representation, and if you want to break it into a frequency, it looks like there are two frequencies. If you put it into a spectrum analyzer, right, you will see two frequencies, like there is one Fc plus Fm. So if this was 2 gigahertz, I said in the previous one, and message is say 1 megahertz, right, you will get a 2 gigahertz plus 1 megahertz, and you will get a 2 gigahertz minus 1 megahertz. But from a time domain, it is just amplitude modulation, just multiplication. This is one way of modulating. This is what your AM radios, right, they use this principle. So there is something called frequency modulation, which is FM. So what does this do? Same thing, you had the carrier signal, but what I did, right, I didn't change the amplitude. Amplitude is remaining same, but I'm actually changing the frequency. So what it means, like whenever my message signal is moving, right, I'm increasing or decreasing the frequency of my carrier frequency around it. So what will happen is the carrier frequency is 2 gigahertz, but it will move, it will drift by whatever is your message signal frequency. It will go from 2 gigahertz plus 1 to 2 gigahertz minus 1 in this example. So this is just a representation equation of that, but if you see that amplitude is same, this is what your FM modulator or your FM transponders do, right? They just don't change the amplitude, they change the frequency. There's something called phase modulation, where you don't change the frequency, but suddenly, right, you're changing the phase of the signal. So phase of the signal is basically, right, if you see, right, there is a sudden jump here, like if you see a jump, like the phase of the signal, right, will change, like it reaches 0 and then you change. Phase and frequency are related, because the integral of frequency is phase, in a different way of looking at it. That's why, right, these two waveforms will look very similar, sort of. There is only subtle difference between these two, because fundamentally here you are changing the period of a signal rather than your amplitude. That's the only thing you need to understand, right? Now we'll extend this modulation. So we understood modulation is superimposing a message onto a carrier signal, right? Now let's introduce what is a digital modulation, because this is what is widely used in all the cellular communication system, right? So digital, anyway, we are all, I think at a concept level, we know digital is all bits, like everything is like a 1-0 bit. There's nothing which is it's like a bit, like how a computer deals with everything, right? Bit, byte, right? So it's a bit. So bit is basically you're just representing the information as 0101 information, right? So this is the digital signal. So same concept applies. Suppose I have a carrier signal, right? So I can modulate this information, like 0 means I can modulate something, 1 means I can change the parameter of a carrier by something. So same concept you do on the top, it's amplitude modulation. Whenever there is a 0 comes in, the amplitude of the carrier wave is different. Whenever there is a 1, right, the amplitude of the carrier wave is big. So you see, right, 0, 1, 1. So 0 is the amplitude is small, 1, 1 the amplitude is big. Again the 0 amplitude is small, 1 amplitude is big. This is one way of modulating. Frequency is same. Whenever there is a 0, I send one frequency. Whenever there is a 1, I send a higher frequency. You see, this is a higher frequency, this is a lower frequency, right? It's moving slowly. So this is one way of modulation. Phase, right? Same, like your frequency is the same, but suddenly I'm jumping the phase. I'm just jumping. Whenever there is a 0, I jump the phase and start my sine wave, whatever, the wave differently. If you see, the frequency is same, but there is sudden jumps. This is called phase. So the difference between AM, FM and this shift keying, right? Shift keying is basically just a digital extrapolation of what you understood in the previous. It's you are just trying to map the digital bits into some information. You are changing some parameter of your carrier signal based on the information signal. That's all fundamental modulation is. So now let's extend this. The way here, right, you can clearly see, right, I can send 1 bit of information by changing this amplitude. What else can I do? This is a simple thing, right? I said 0 and 1, correct? Suppose, right, what I can do is like I can map 2 bits, right? If you take 2 bits of information, right? So 2 bits, right, can have 4 levels, right? Truth table wise, you have 0, 0, 0, 1, 1, 0, 1, 1, 4 levels. Suppose what I do, right, I can actually do 4 levels, right? I can introduce 4 levels of my amplitude here. That is one way I can do. Similarly, right, I can combine 2 bits and I can actually change this frequency not just by 2 values, I can change it by 4 values. So this is all like ways of improving the number of bits that you can transmit. Is like a multi-level. This is what I have shown here is simple amplitude shift keying, where the bit says there is one amplitude to another amplitude, phase is one frequency to another frequency, but multi-level means you can do multiple levels. I can have so many levels of amplitudes, right? I can map, and similarly so many frequencies I can map, right? And so many phases I can map. We'll see what that entails. Basically, right, it's all trying to pack more bits. And now we will relate to what it is helping, because finally we said, right, I want to pack more and more data bits, but I want to do it in a lower bandwidth, because we always knew, like, we need more and more bandwidth to send more bits. But how do I actually reduce the bandwidth and send more information? That's where this is leading to. Okay, so how do you increase the number of bits transmitted? If you see this, right, this is a simple example that shows. So, so the windows, the vertical lines, right, are all the symbol times. Like when I say 1, we saw, right, 1 Mbps, that means like within 1 second I am sending 1 million symbols. So 1 symbol time when I want to send an information is like 1 by 1 millionth of a second, right? That's a 1 microseconds actually. That's where the information is changing. So that's, let's say we take a information where it is 0, 0, 0, 0, you want to send this information. You take the next picture where what I do, right, I actually, or let's go to so the next picture where I combine the bits like 0, 0, 0, 1, 1, I just combine 0, 0, right, 0, 1, 1, 0. But if you see the vertical level, these were moving only by 2 levels, correct? Here you can clearly see there are 4 distinct levels here, correct? I have moved 4 distinct levels, and then I have actually mapped 2 of these bits to 4 levels, right? But if you see the time axis, right, what I am able to do, I am actually able to send 2 bits in twice the time, right? Same concept when you go back here, if you are able to send 2 bits in your same 1 microsecond, what I have actually done is you compare the first plot and the last plot, your time intervals are same. The time interval, right, when something is changing, that is same between the two, first and last, but you are actually sending double the number of bits here compared to this, right? See here, right, 0, 0, 0, 1, 1, 1, 0, whereas here, right, 0, 0, 0, 1, 1, 0, you have finished here. This has taken so many symbols to send this information, whereas here by doing this, right, within the same time, this time, I have actually sent double the number of bits. So what is this mapping to? From a time perspective, we are able to send double the amount of information, right? You are increasing the data rate. So again, we'll come back to what we said, right? We said the time, like how fast something is varying over time, the time axis is actually deciding the bandwidth. We saw, right? If something is moving very fast in time, it has a larger bandwidth. So what I have done compared to this and this, I've actually increased, like the blue curve is the bottom one and the red one is the top one. So what I have done is, right, I have actually increased the bandwidth, right, for sending that information, or in another words, within the same bandwidth, right, I can send twice the amount of information by coding information in the voltage level rather than in time. Because we know all, if something has to be faster in time, we know I need larger bandwidth in the larger bandwidth in frequency. But why not I map more things in my amplitude so that I don't change my time axis, but I pad more information. So that's where multi-level modulation comes in, where you code information where you map more bits into more levels of amplitude, but you don't change, your time axis is remaining the same. You're not increasing the speed at which you are changing, but you're actually giving more information in the other axis, right? Okay, so this is another concept that sorry, that you need to know. This is quadrature modulation. We'll see what this means, right? So as I said, right, the two fundamental things that are very key to signal processing are sine and cosine. I think anything you want to do, right, it can be broken up into this. So clearly, you know, cos and sine, right, very simple trigonometry, you know, cos and sine are actually 90 degrees phase shifted. That means like when cos is 1, sine is 0, when sine is 1, cos is 0. So in some way, right, you can look at it, they are orthogonal. Like whenever one is going 0, the other guy is going up, and when one is going 1, the other guy is going 0. It's sort of orthogonal. So what does it involve is, if you have something which is orthogonal, you can actually, they don't interact with each other. When you say something is orthogonal, right, they don't interact, and you can uniquely decode what these two informations are, right. So if, I don't know whether you are familiar with complex numbers, right. Complex numbers also, you have some real number and you have a j or an I and you have a complex number. Why is that? Because the j gives you an orthogonality, and you can actually change a real number part and your a plus jb, right. You can change a, you can change b, you can sum and send, but later, right, I can decode what that a and b are by sending in the same space. So you take cos and sine, assume, right, we'll what does it mean? If you have cos and sine, if I say cos plus sine, right, if I just add both, right, it looks like as if it's one of the it's equivalent to a cos or a sine shifted by 45 degrees. If you write the trigonometry, right, you will get cos theta plus sine theta will be either some sine theta minus 45 or cos theta plus 45. Effectively, it looks like one information, but depending on what is the weight of cos and sine you give, right, you are getting different phase shift. You can decode. So at a fundamental concept, right, you can assume like cos and sine are orthogonal. You can send two information in the same bandwidth. It doubles your bandwidth for the same space that you are occupying, right. So what does it entail? So we saw that, right, 2 bit streams we saw, bit stream we saw, like bit stream I take, I modulate a carrier frequency, right. Now what I will do, right, I will take 2 bit streams, and the carrier frequency is not a single carrier frequency. So there are 2 carrier frequencies. Like what are the 2 carrier frequencies? I create one carrier frequency, we said 2 gigahertz, but I will create a cosine version of it, I will create a sine version of it. 90 degrees phase shift is sine version. So I have a cos 2 gigahertz and I have a sine 2 gigahertz, and we know they are orthogonal. Now what I will do on the cos 2 gigahertz, I will do the modulation. Like we can do any modulation that we saw earlier, like ASK, PSK, FSK, multi-level, anything you can do. Same thing, right, you repeat on the other stream. You are doing it on a sine. Then you sum both. You sum both of those signals and then you send it out, right. When you send it out, now if you look at the frequency spectrum, right, we said finally we are looking at frequency spectrum. The frequency spectrum will not be double, because the cos and sine are orthogonal when they add, right. Like I said, right, cos and sine when you add, right, the periodicity or how fast they are changing, right, that's not going to change. If you add cos and sine, you said you're still going to get cos with 45 degrees phase shift. But what is it giving? The bandwidth is the same, but you actually can give more amount of information. Like cos you can modulate, sine you can modulate, they coexist in the same bandwidth and you can demodulate it. This is one of the very fundamental concept, right, is in all communication systems. You forget just the cellular communication, any communication system, right. This quadrature modulation is a fundamental concept that is used, because it is a free thing where cosine and sine are orthogonal, and that you exploit to send double the information in the same frequency band or same space that you have in a frequency domain, right. That's the space. In a communication system, right, like real estate, right, communication system is the bandwidth or the spectrum is the space. So you want to maximize that, right. This is the default thing that is done. On top of it, right, you do multiple things, but this is a default that is done for any communication system. This quadrature. Okay. So now we'll extend that concept, right. We said what is QAM, because these are some of the words, right, that is very related to how the evolution of mobile technology has moved, like 3G, 4G, 5G, right. People will talk like, okay, 5G uses 256 QAM, 4G uses 128 QAM, and 3G uses like 64 QAM. What does it mean? So fundamentally they are saying how they are modulating the information. So here if you see this graph, right, so what I have plotted, right, I and Q. So these are the like a complex like sine and cos, like I told, right. So what I can do, right, the cos function I can modulate it, let's say with 4 different amplitudes. We saw that in the previous one, right? ASK, where you can do multiple levels, like you can map multiple bits to multiple levels. So within cos, right, I can have multiple amplitudes. Within sine, I can have multiple amplitudes. So if you merge all 4, right, so I have 4 combinations, 4 possibilities on cos, I have 4 possibilities of sine. So effectively, right, I have 4 into 4, 16 combinations of the waveform that you can construct at the output. So this is just a pictorial representation saying 16 so when you have different scaling of cos and sine, right, you have 16 possible unique values. So this is what it says. So what this means is, right, in the same bandwidth, I am actually sending 16 values, which is equivalent to 4 bits, like 4 bits is equal to 16 truth table values, right. So actually, right, you are able to send within the same bandwidth without changing the frequency, you can actually send 4 times the information, and you can keep increasing this. Like if I map the amplitude level to instead of 4, 8, right, on both cos and sine, then 8 into 8 instead of 4 into 4, 8 into 8 will be 64. So you can see more finer dots, right. It's like a 4:4 array. You can have 8 by 8 64, you can have 16 by 16 to 256. That's what is QAM. So fundamentally, at least the 5G communications that they use, right, the kind of modulations they use, it means 256 means this is 16 by 16. That means like they are actually mapping 8 bits in the same bandwidth by modulating your cos and sine by 8 different values. That's what it means. But okay, we'll go back to that. We'll see what is this in a later perspective. But this is what. So the one thing you can clearly figure out is that as you keep increasing this QAM, right, on the top, right, they are going to be more denser. You will have more points, and the points are going to be very close, right. Within the same area, I have to put more. 16 by 16 means there will be a lot of points here. The spacing between the points will be very close, right. That's natural. Like you will have more points within this. Your grid will just be very denser. But these are the different, see what you have to code, right. This 16 information is actually coding, is telling me what are the 4 bits that I have sent, correct. If so, I have to actually figure out where what I got, whether this is here or this is here or this is here, will map to that information. If it gets very crowded, right, the spacing between the two is very small. Now we talked about, right, there is noise, there is so many impairments in the channel. Something, right, moves this around, because this is not the information that is coming out as it is for you, right. There's somebody is adding noise. That noise looks like as if, right, it moves this. If there are two closely spaced signals, if let's say noise moves this to this point, then I will detect this signal as this signal, this bit, this symbol rather than this symbol. So then your information is lost, right. So that's the challenge. Like when you keep going to higher and higher QAM, you can pack more bits into the same bandwidth. But the problem is, right, you will not be able to decipher that information. You will make errors, right. You need better systems. So this I think so the current, this is just, meaning I'm not going to go to the theory of this. This is more like an extension of it, where it's called OFDM. I think this is the only standard that is used in most of the 3G, 4G, 5G systems nowadays. It's called OFDM, where they break the channel into multiple carrier. I said cos and sine, right. They actually make so many carriers which are orthogonal, and then they they modulate each of these carriers depending on the information. Meaning I'm not going to go to the details, but just to tell, right, OFDM is actually an extension of this QAM and quadrature modulation with multiple carriers, which is actually the standard. It is a standard that is used in most of the communication systems now. We can see like it entails, meaning it avoids many things, like this noise part I was talking about, right. This way it actually helps alleviate some of these problems and improves the immunity in detection. I think I'm not going to go into the details. It's more like signal processing in digital domain, right? Just to give a summary. Okay. So now the next concept that we need to see is mixing, right? So mixing, right? What does it mean? Like I said, right, information has to be moved from one frequency to the other, because many of them have to coexist. So what do you mean by mixing? Mixing is basically, I have this information here. I wanted to shift it to a different frequency to send it across the air, right. So the same voice information, let's say Wi-Fi has to do it at 2.4, your mobile phone has to do it 3.5, right. So somebody has to shift that information and send it through air. That's called mixing. It's like up or down conversion. So you can clearly see, right, the information from here shifts. I want to shift it to this, right. How do I do it? Simple thing is like simple multiplication. You take time domain, you take a cos and you multiply it with another cos, right? This is the carrier frequency, this is your message frequency. Cos A, cos B, you know, for trigonometry is cos A plus B, cos A minus B, right? Clearly you can see there are two frequencies that are generated. One is the sum component of what you mixed, and the other is the difference component of this. That's what this shows here. So you take this information, it goes into two places here. That's what a mixer or a mixing thing does. So you have moved it, but you have created, you wanted one, but you have ended up creating two, right? I want to move this to one, but I have created a copy of it because of the natural function of what a mixing. Mixing is just multiplication, right? Now how do you get rid of one, right? I want only one. So that means what? I need only this plus, let's say. I don't want minus, right? I don't want this. From a trigonometric entity, right? Simple thing is, how do you get it? You take this equation, instead of doing cos A into cos B, you got this both. But let's say I have somehow, right, I'm able to do sin A and sin B also. Cos A into cos B plus sin A into sin B is actually only one, cos A minus B. So what do you need? You need one more. This is the mixing we said is multiplication. This is another mixing, but this is doing on the phase shifted signal. I said sine, right? Sine is just a 90 degrees phase shifted version of cos. If you are able to do this, then you actually get one. So this is also an important concept that is used in mixing. Like usually when you want to move, right, you don't want to move into two bands. I want to move it to one band. So what you do, you have to do this. Like you take a signal, you multiply them as it is, then you take phase shifted version of each of them, create a sine component, multiply, right? Then you will end up with only one side. You will not end up with the other side because you don't want to waste information in free space, right? This is premium. So this information I want to pack it. I don't want to have a copy here, one more, and then waste that space and then waste my spectrum usage. So this is another concept that you need to understand is mixing. What is mixing? Okay. So now coming to data converters, right? So all we know, right? Real world, all sensors are analog, like speed, voice, any sensing, everything is analog. But finally, power of digital, right, is computer. Everything is digital. It's bits, bytes, right? How do you convert? So you need somebody to convert this analog to digital. That's where data converters come in. So basically a bridge between analog and digital. So an ADC is an analog to digital converter which converts analog information into bits. A DAC or a digital to analog converter does the opposite. It takes the bits and converts to analog information. This forms a critical component of any communication signal chain because you want a digital processing, but your real world voice, whatever you are doing in air is all analog, right? There's nothing like digital. So so these two are important components. We'll see as we get to a signal chain, right? ADC and DACs. We call it as ADC or A to D, which is analog to digital, DAC or D to A, which is digital to analog, which is short form, right? So this we saw. Okay. So now once you have an ADC, right, how do you convert analog to digital, right? So you need a time base now, right? Analog signal is just free moving. I'm discretizing in time and amplitude. That's what a ADC does. So you need both. You need to discrete time. You're not representing it in infinite time. You're saying time slots, right? That's what discrete time signal means. So your waveform has to be discrete time represented, and also amplitude is not full. You have discrete levels that you want to define analog. So any ADC or DAC, right, has two things. There is a sampling rate, which means what is the spacing of signal that you want to represent, and the other is resolution, is like how fine you are representing the analog waveform. Like what is the error in, it's not like if you have like this is the level set, because discrete means you can't represent so many, you can't represent the analog information in infinite precision. You need some finite precision. So there are two things. You can say quantization in time and quantization in discretizing in amplitude, right? These are the two things that you have to be familiar with a data converter. So what is sampling? So we said, right, the ADC or DAC needs a sampling, right? So now how do I decide what is that sampling interval or the discrete time, right? So that is basically decided by something called Nyquist theorem. I think maybe some of you will be familiar, some of you will get familiarized as you go through your courses. So what this specifically means is, we said bandwidth, right? We saw signal bandwidth in the first foil. What is a bandwidth? Your rate of sampling or the clock rate at which your ADC or DAC converts should be minimum twice the amount of that bandwidth. We'll see why that is needed later. So that is what decides the sampling rate of your data converter. So simple example, right? You take this is your continuous time signal sine wave, right? I decide, right, my ADC is actually going to sample this information, means I'm going to look at the sine wave only at this point, then next here, next here, next here. Clearly, right, then your ADC is just giving this as your output, like sample, 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 sample. But that is like a fixed value. You are getting only sample of this. But at the end of it, right, you actually sent a sine wave. You are not representing the sine wave. You completely lost that information. It's just saying everything is static. That's what you're doing. Same thing, right? Let's say you start increasing the frequency or reducing the time. You sample once here, you pick the data here, you look at it here, you look at it here. At least it looks like, okay, something is high, something is low, something is high, it knows like signal is moving. You extend it same. You put many points, like that means you are sampling higher and higher frequency. Then clearly, right, you say the value is moving from here, 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 here. It is actually a faithful representation of what you wanted to send, right? So the higher and higher frequency, your signal is faithfully represented. But if it is, so this is where this 2 times bandwidth comes. If you are not able to, because right here you see, right, I am actually sampling it at the same frequency of my signal. It is not 2x. Like I am sampling here again. Next time, right, I am sampling once. Every period I am sampling only once. Whereas here, every period I am sampling twice. Minimum if you sample twice, right, at least you know the signal is changing. And more than that you do, right, you get better representation. Lesser than that, right, you have lost the information. Right, you are not representing this information. So that's what is in frequency domain, right, looks like aliasing. Aliasing is basically this information is not a representation of your information, right? So this is the frequency spectrum. It just copies and then folds. So meaning at a concept level, right, you understand that is enough. Like it folds. This is your sampling rate and this is your bandwidth. This blue end curve as your bandwidth. If your Fs is twice this, right, you are exactly matching this. This one doesn't match merge here. If it is lesser and lesser, right, you can see these things are merging, right? So this keeps coming here, then this green will fall over blue, and that is equivalent to that you are not representing the information. So you know your rate has to be double this. This is bandwidth, right? This should be double. This is your Fs rate that you need to remember. Okay, so similar thing. I think I'll skip. So DAC also is the same thing. You have when you have digital information, you have copies, and if you don't run the DAC at twice the frequency, same thing happens. This comes and folds here, right? So you need more and more rate so that you actually only have a faithful representation of a signal rather than all the copies or some bad representation, because you're trying to not represent the signal in its full time and voltage. You're trying to represent it over time. Like within this something has moved faster, right? You will not going to represent it. You have lost that signal. That's where this higher and higher rate frequency comes in, right? So this is okay. Okay, so now I think we have mostly looked at the basic concepts, right? Now we'll come back to what a cellular signal base station looks like, right? And so if you see, right, a signal chain architecture, you have an antenna, and this is like a switch. We'll see what this is at a later point. This is not very important for the signal chain. This is an antenna, and you have a receive, which is in the green, and you on the bottom there is a transmitter chain, right? So this any base station, right, you have to send and receive information. So this is the sending part of the information, this is the receiving part of the information. This we'll see at the later point. I'll talk about in one foil about what this chain is. Right now let's ignore that. There are two signal chains. You have a receiver, you have a transmitter, and you have two sections, transceiver and baseband, right? We'll see what this is. Transceiver basically is a transmitter and a receiver. That's all, it's a transceiver. But this is basically the analog front end which converts the analog information into raw, some form of digital information, which includes signal conditioning. We'll see what it is. It will include some gain, something in the curve. Finally, it will end with a analog to digital or a digital to analog converter. Boundary is transformed to digital. That's it. But then the modulation part, how the symbol is mapped, the QAM and other things, right, all are done. Once it's all in bits, right, you do it in digital. So that's a baseband processor. So if you take a cellular base station, there are two units. Usually they are called radio unit, which is transceiver. Then there is a BU, which is a baseband unit, right? These are the two different boxes. That's it. Usually they make two boards. So this is all DSP, signal processing and stuff that you do in a processor. This is all analog, right? That is the, so baseband level is all in digital domain. So for the scope of this talk, right, we are going to talk a signal chain which is hardware signal chain. We are not talking about what is there inside the digital, what is the digital signal processing. We are going to look at a transceiver, what are the components of it, and we will build why a particular component is there and why it is needed with all the things that we have assumed earlier, right, or we have gone through some basic introduction so that we can relate to it part, right. So this is what we are going to start. Okay, so let's start with a transmitter signal chain, right. Transmitter signal means you have to transmit information, right. That's what the transmitter signal chain is. So this is the same thing that I have shown on the top. There are different blocks, right. We will see what each of the block does. So transmitter signal chain is, you have your baseband processor, which we said we are not going to look at it. It gives you some information. It has done some QAM and everything. It has given you some bits that you want to transmit. So now what you have to do, this transmit, you have to, the information you have to take it and put it into air on antenna, right. And we have seen many things that we want to do. This is digital, finally this is analog, you have to have a converter. Then you need, we said like you can't have a low frequency information directly sent on air, you have to move it to a carrier frequency. Then we discussed about what is mixing. So that's where all of these things will come into picture, right. We'll start one by one, we'll start. Okay. So this is the digital data that is there from a baseband processor. Any digital data, right, digital I said has copies, meaning at a concept level, just assume blue is the information that I want to send. But anywhere, whenever there is a digital, right, digital means it's discretized in time. In frequency, there will always be copies, right. But they are all copies of the same signal. That's how the digital deals with it. But once you reach to analog, you don't want these copies. We'll see why it is. So this is the information that I want to send on to the final air. This blue thing has to come at on air. That's what I want to do. But the digital starts off with this. There are a lot of copies because it's the way digital is, right. It is it's repeating because digital doesn't know after every clock, right, the sample is repeated, meaning you can't differentiate the information. So to that concept, you will understand that. Then D2A, right. So this IF, right, is the frequency. I have just taken a case where, let's say 2 megahertz or 3 megahertz or 10 megahertz, right, anything you want sent to information, this is the center frequency, meaning so there is a band around it, this is the bandwidth. Bandwidth is this, center frequency is what this is. Finally, this I have to take it to any carrier frequency, 2.5, 3.5 that I want to do based on the antenna size, right, that's what I want to do. So what does the DAC do? We said DAC is converting digital into analog. So the process of doing that, right, DAC, what it does is, because it's converted to analog, it is actually, it will try to filter some part of this image. So there is a filter. So the way you look at it in the DAC, you run it at higher and higher frequency. We saw in one of the previous foils, right. So it tries to cut the copy, because if you see, right, there's a copy at Fs, it will try to filter that copy. So that's why if you see this image, there is something that is getting filtered. There is something it's coming up, but exactly at Fs, right, it will filter. That's what a DAC does. So the larger and larger you do Fs, right, you will cut that better. It's closer to this, right, you will not get this protruding portion will be far away from your desired information. That's the importance of running this at higher and higher frequencies. This entire thing, right, if we can see that Fs moves here, this remains the same. Fs is moving farther away. So this unwanted image is at a farther location compared to your desired information, because that's what we want. We don't want it to be closer. Then your receiver will pick that information. That is so don't worry about this. We'll see what this is later. Now I have converted the digital information to analog, which is done by DAC, right. This is still at your 2 megahertz, 10 megahertz message frequency, right. Now I said I want to move it to a higher frequency, carrier frequency. This cross block is actually a multiplier, right. That's a mixer. We saw what mixing is. Mixing is basically up conversion or down conversion, both. In this case, I want to do up conversion because I want to take a lower frequency information, send it to higher carrier frequency, right. That's what I want to do. So what the mixer does, we saw that, right, in a mixer, when we do a simple mixer, it creates two components, one plus and one minus, right. You started off with FIF, and let's say the clock frequency that I choose is F. I am just taking an example, FLO minus FIF. This frequency, right, is FLO minus FIF, just as they are all just names. When I mix, right, we will get two components, FLO minus FIF plus IF plus FIF, FLO minus FIF minus IF. So that's what, if you see, right, FLO minus 2IF and FLO, right, this FLO is RF. This is what I want, right, but this I get because I am doing a mixing. So we saw, right, one way of doing different mixing is if you do this cos and cos and sine and sine. We said cos A plus cos A cos B plus sine A B, right? I can get only one sided information. For that, right, I need one more chain here. We'll see that in a later part, right? That is the evolution of architecture. This is the simple legacy architecture that I took. Simply, if you want to mix, you'll just do a multiplier, it will create two components. This is unwanted component. I want to send only this in air. I don't want this in air, but this has come right now. So what will you do? There is a filter. So filter is basically, right, it will just knock down, it will select the frequency component from whatever it's, right, it's a filter. So filter is one of the key aspects of any communication signal chain, because you want to filter and look at only what is required. You don't want to look at the entire spectrum. That's what. So what does the filter do? The filter has to be designed in a way where it passes this but filters something which is 2 times FIF away. It has to filter. You see, right? It is knocked. So the challenge in it is the frequency here is at 2.5 gigahertz, and we said this spacing, if you see the center of the red curve to center of the blue curve is only 2 times FIF. The spacing between this 2 times IF. If you start with 1 megahertz FIF, this is only 2 megahertz. But let's say FLO, the carrier frequency is at gigahertz. So typically what it means, though I have drawn the plot to be this much, right, it will in an actual scale, right, this is gigahertz, this spacing is megahertz. If you draw in a linear plot, right, this will look very close here actually, right, this is in megahertz, this is in gigahertz, like 1000, right. So it will be very close. So the challenge in a filter is at 2 gigahertz, it has to quickly filter anything which is 2 megahertz away. That's the challenge in any filter. Filter, if you want the cutting part, right, you want to, how far away you want to cut, right, at that frequency, it's a relative portion. If you are running at some frequency, you want to cut a frequency which is very close as a fraction of your center frequency, the filter gets very complicated in size. There are many filters like SAW filters. You need bulky filters. Actually, your base station itself will be dominated by 40% of it, right, will be filters. So this architecture has that problem. The only issue, right, so what you will do, you will have to reduce your RF, or you have to have bulky filters, right. So that's a challenge, just for you to introduce why the later architectures, right, are trying to evolve things out of it, right. We'll see what is the reason. So the thing to understand is your filter at higher carrier frequency, and this, if it is narrow, then it's a challenge to implement a filter, but you need a filter, otherwise you're sending, your allocated band is only this, but you will send this, you will have to filter it. Then you have something called a power amplifier. So finally you have done all this, but you have to blast that on air, right. You have to give enough power so that it transmits to long distance. So that's what is done by a power amplifier. So power amplifier is just a amplifier which just blasts power. Whatever is the signal just gains up and blasts the power. You can see the signal just, you have filtered and this is just blasted out, right. Now you see what all you have got here. You have got some information which came from the image which got filtered by the DAC. You got something from here, because if you are mixing, you filtered. But these are the things, right, are the residual that you have created, right. But you are supposed to be ideally sending only this, right. So you have transformed the information from FF into your carrier frequency. This is what is going in air. But these are the other things that you have created. Now we will see what are all the impairments or the effects of this, and what the standard or your regulatory body, right, they will force some things. Like I said, right, initially there is interference, because this channel is not allocated to you. Somebody else has bought this channel, like Airtel is allocated here, Jio has got this, right. You can't keep sending some information here, it will corrupt his thing. So there are some standards saying, right, this has to be below a particular level. You can't send information here above a particular level. You can't send something very close to your band, right. These power levels have to be lower. That is all mandated by a standard, like a ITU telecommunication standard, right, sets these standards. These are all specific to 4G, 5G. They will set the level of what you can transmit. So that decides the architecture of what you want to do, the amount of filtering you need to do, how much you want to run this. I was telling, right, FS, how much you want to run this frequency. All that is actually an after effect of meeting these strict specs. You will have to change your architecture, right. That's what this. So now this gives you a brief overview of what are all the blocks, right. So now this one, right, is a PLL. PLL is actually phase clock loop. You can assume this is giving a clock. I said whenever you have a DAC or a ADC, you need a clock frequency to convert, right. So this is given by this. This is the block which generates the frequency, whatever you want to do, right. Same thing, there are 2 PLLs. So this rate is only operating at 1 megahertz. You don't need a gigahertz frequency. Whereas here, I said you have to multiply the signal with either cos 2.5 gig or sine 2.5 gig, right? That cos or 2.5 cos or sine 2.5 gig is generated by what we call radio frequency PLL. So RF is high frequency PLL. Filter we already studied. What is DSA? DSA is only like it stands for digital step attenuator. The way it is drawn, it's very simple. I have an ADC, I have a mixer. This is to set the amplitude. Like you can just gain up or adjust the amplitude. You can increase or decrease this amplitude here. This is a block, just adjust the amplitude so that you can provide that signal to the PA, right? PA has to put some power. It needs some particular amount of level signal here. But where do you change that signal? If you want to high or more, this is a block which just adjusts the signal depending on you want larger range or lower range, right? You will adjust the signal. Like suppose you are talking to someone very close, right? The standard allows that this signal will be attenuated, so you don't blast too much. You would have seen in your Wi-Fi, right? You can actually change the power level of your Wi-Fi. If you have a room which is like 3 blocks away, you will have to blast power. You will see some dBm. You will see like minus 40 dBm. If you set the channel, or you can go to minus 60, then your radiation will be lesser if you go to lower power because you are around your Wi-Fi. It's similar concept. So this basically digital step attenuator only does the change of what power level you want to do. Okay. So now we'll come back to what are the impairments. Okay. So I said, right, this is the wanted information, but you start sending something on the unwanted part of the information. So we talked about the two things in the previous slide. One is the DAC rate, decides the first unwanted information filter. The other one is the mixer, which actually mixes the signal and you have to filter, right? Now there are more aspects to it. So this is one of the key aspect in any transmitter is called ACLR. ACLR meaning the jargons might look very difficult, but it's very simple. I'll try to explain. It's adjacent channel leakage ratio. So what this means is this is your channel that you have been allocated. Adjacent channel means somebody is occupying the adjacent channel. Some other user is occupying the adjacent channel. Adjacent channel leakage ratio. That means like you are sending power here, which is your information. There is a spec on how much of this, right, can leak here, right? That's a leakage ratio. So they spec saying if this is your send, you can't send more than 1,000th of your signal, right, here. That is an adjacent channel leakage ratio. This is a spec. So what all specs that decide this? So one of the things, right, you can clearly see is the filtering thing we saw earlier. The other thing is non-linearity, right? We'll see what non-linearity is, right? I'll just introduce this. Non-linearity is like any system, right? You give an input, you look at an output, you plot V out versus V in. It should be a straight line, right? If you increase the input by some amount, output should increase by the same amount. It's like a unity gain slope, right? If your input was 1, output was say 1. If you gave input of 1.5, your output also has to be 1.5. But typically all circuits don't behave that way. They will do till a particular point, 1 they will give 1, but let's say input went to 10, right? Output should have already gone to 10, but output will not go to 10. Output will go to 9.8, 9.5, because always there is all a limitation of all your circuits are running on some supply, right? You will have to provide supply to the device. Once the supply to the device is there, you can't have, once it starts getting closer to the supply, right, things are not ideal. So things will start to saturate. That saturation is what is called nonlinearity. So this, I think mathematics is just a thing to explain. So I can model, if let's say, right, you put in your Excel, right, you just try to randomly draw input to output some curve, and you can do a trend line fit in an Excel. If you any point, data set point, right, I can convert to a trend line polynomial fit. When you do a polynomial fit, it will say y is equal to some number into x plus some offset, which is your offset, plus if you put more and more polynomials, right, any curve can be fit into higher order terms. What is the residual error? You have a linear term, you will have a cubic term, you will have a square term, you will have a fourth order term, fifth order. So any curve, right, can be fit as a polynomial equation. That is understood, right? Any curve which is not linear, if you have a linear curve, you can just say y equal to alpha x. But if the curve is not linear, it is bending, you can always represent it as a polynomial. Assume, right, most of the devices are going to give you square and cube if you fit, right? That's the nature of the saturation or the curve that is created by all the circuits like DAC or PA or whatever. So simple thing is, if you have two tones, right, sum of two signals that I have given, cos omega 1 and cos omega 2. If you put it to it and then do a cube or a square, right? So you do cos omega 1 plus cos omega 2 square, normal thing, a plus b square, you do a square plus b square plus 2ab, So you will get cos square, you will get of both, you will get 2 cos 1, cos omega 1, cos omega 2, you will get all the combinations. You can write it, I think you can think. The fundamental thing I want to do tell is any square or cube on a sine or a cos information with 2 frequencies creates mixing components. It creates 2 times omega, 3 times omega, it also creates omega 1 plus omega 2, omega 1 minus omega 2, it creates 2 omega 1 minus omega 2, 2 omega 1, that's what this equation states. You can just take 2 cos omega 1 2 plus cos omega 2 2, do a cube and then try to break it out into residual cos components, you'll be able to find out. So what it means, right, your signal is having so many tones, once it passes through a non-linearity, the 2 omega 1 minus 2 omega 2 are actually, if you see in frequency array, they all fall here, because 2 omega 1 minus 2 omega 2 is what? Omega 1 minus omega 2 plus omega 1, right? So omega 1 plus omega 1 minus, so this is your band, things will start fall around it with the difference between the two. So your non-linearity is actually creating flare-ups, this is called spectral flare-up in a communication system or whatever, right? So what is it doing? The non-linearity is actually spreading this information into your nearby bands. This is not decided, so you have to meet this particular level. So there is a spec on what the non-linearity has to be, right? So that is one key aspect or an impairment in a transmitter signal chain. The other is error vector magnitude. Error vector magnitude is basically meaning this is little complicated, so I'll just tell it in a word where we saw about this constellation, right? We saw that you can have that 4 by 4. This I have taken a case which is just 4. It's 2 by 2. These dot points are the ideal ones. But what will happen is, we said all the while, right, we've been telling the clock used for mixing is a single frequency. I say I'll mix a 2.5 gig clock, I'll generate, but nothing is ideal. You use a PLL to generate a frequency, it will not create one tone. If you put it into a spectrum analyzer, right, it will have some spread. Nothing is like ideal. So what this does is, because your frequency is not fixed at 2.5, it is like 2.5 plus 0.001, 2.5 minus 0.001. Effectively what it does to the constellation, these 4 ideal points, they'll start to deviate. And this is not deterministic, it is random. Like I said, like thermal noise is there, something is varying. So your frequency actually is varying over time. So it means like, it look like the symbol, right, is moving a little bit here and here, here and there around this. These 4 points are not ideal. So now, right, if we saw, right, if these points are very close, because of this, right, one point can come close. Here it is not, meaning it is shown such that this point, right, doesn't come closer to this point. But if you are a 4 by 4 or a 64 QAM you go, right, there are so many dense points. One point, because of this thing moves, right, it comes and hits the other one. So this is a error vector magnitude is a representation of what that error is, how much it can move. So this decides how many bits or whatever you can send, right. That is the other key concept of a transmitter. If you see, right, any transmitter thing, these are the two things. One is spectral marks and the other is EVM. These are the two critical specs that decide. One is decided by non-linearity, other is decided by noise or phase noise, what we call phase noise. It's like a frequency, the error in the frequency of your mixing, right, it's called phase noise. So I think at that level that is enough. I think we'll not go into too much of this. Now let's go to the receiver signal chain. This is little bit more interesting. So you can see here you have an antenna, forget the switch or the duplexer. We'll see, right. So there is a block that comes in, you have to take the information from air and then you have to put it to baseband, the opposite of what you did earlier. So we'll go through again one by one, right, what is required. So clearly here you see, right, because it is air, right, I can't say there is only one information. Air has all the information, like many users are transmitting. So the desired information is blue, then you have something which is residing at some other place. I'll show what it is. These are all unwanted information. So I'll call it image or whatever, right. I'll see why I call it as an image. The key thing to note is this is your 2.5 gig around it which you have. This is what ideally I have to take the blue information out. That's the goal of the receiver chain. But you have so many things. You have something which is at this frequency, like something shifted, and you have a 2 megahertz away, right, you have something else, or you have an image, what we call an image. We'll see why that is important. So these two have to be taken out and you have to take this information out. That's what is the goal of this. So first block is a low noise amplifier, which is basically, as the name suggests, it's an amplifier. As I said, antenna systems, right, antennas are all passive circuits, right. I said there is thermal noise, we'll see what it is. So before you give anything to your following circuit, right, you have to gain them, you have to amplify that, because otherwise it's very feeble. Antenna is very feeble, signal it will receive, because you are receiving some very far end signal, right, you have to gain. So the amplifier is just as a name, it takes everything, magnifies it, like how the power amplifier was doing on the side. The only thing here is low noise amplifier, because it doesn't add noise on its own. It will try to gain up the amplifier without adding noise. The bottom thing is noise, right? It will try to add the lowest amount of noise, try to gain up. That is the what we call as an LNA. Now again go back to it. I have a filter. So specifically what I have done is, this filter is chosen such that it filters this image, what I have shown in this pink color, which is at IF frequency away. Why that is needed? Again you can relate, right? When you mix, we said when you mix, right, it sums up two frequencies and subtracts two frequencies. Same thing holds. When you do mixing with a frequency to bring it to something, both of, see, this can move to this side, this can move to this side. Actually you want this to move to some lower frequency or mixing, because mixing always just plus and minus. This is minus, it will do some other frequency, take plus and put it on the same band. So that's why, right, you need to mix this, you need to filter this, or we have to do the cos and sine we talked about, quadrature modulation, where only thing this shifts here, this shifts here. If you do a normal multiplication, this will shift here, this will also shift here. This will ride on top of blue, right? Then your signal is corrupted. You need a filter. So that is why this filter specifically knocks off this. Now you will see what happens after a mixer. So once the mixer is there, what happens? This entire thing which was centered around RF now has got back to IF. IF is our thing, right? You see the entire thing is shifted. If you see the entire thing is shifted down here. If you have not done the filter, this should also come on top. So I have put a small, you see on the bottom, right? This pink color, some small residual is there. It is there. It is filtered by this. If you don't do this, right, this pink will just take over the blue. You are not getting, it's corrupted. So you are actually filtering this part, right? That's just to show that there's a filter residual that is coming. So this needs to be below your blue level for you to detect. But now what has happened is, as I said, right, mixing, this also moves to the other side. So you create something which is twice that component, right? So this, right, is not wanted. This is ideally it's the same information. You don't want it because this, the reason for this is the ADC, right? We said ADC, when it has to sample, the sampling rate of the ADC should be twice this signal bandwidth, which is this. But if your signal bandwidth is, now if you created this, right, your ADC sampling rate should be twice of this edge. I don't want to run the ADC. I've already got the frequency of information, just a copy, right? If I want to take this, right, I need to run the ADC which is much higher frequency, which is a problem. So what I need is, I need another filter which will filter this part. Then now this is the signal that goes into the ADC. The ADC, as we saw, this is the bandwidth of the signal. The ADC just has to do double of this frequency to get me, to make sure it is faithfully representing. We saw that Nyquist theorem sampling, right? That's what it does. Takes this in digital, right? It's just a copy. Now in digital, you can just go strip out this blue by a digital filter, because these are very close. The blue and green are very close. You can't filter them. Ideally, you could filter, but if you, like I said, no, if you want to filter very close compared to your center frequency, the filter becomes very big or very complicated. So usually, right, some part of this close-in filtering is done in digital domain in DSP. So now when the digital takes off, right, you have got this blue information. So you started off with something with interfere image by doing a LNA mixer, filtering, then ADC, you have got back to an image, and the remaining baseband processing will take it, and you have got the blue information. So both sides, at transmitter also we saw blue went to carrier frequency. Now I have extracted the blue information Y. So these are the key components. You see LNA, mixer, filter, A to D or D to A for a transmitter chain, right? These are the key aspects of any signal chain. So again, we'll see what are the RX parameters. So this I said, right, what is sensitivity? Sensitivity is like the lowest signal that you can detect in the presence of noise. I said, right, initially, analogy I gave, like people are talking and then one guy is talking very feeble, and the ability of the receiver to pick up that feeble signal from somebody in the presence of whatever sound you have a construction sound or noise, it depends on that person's sensitivity, right? If one guy might do it, very sensitive person who can detect it, some may not be able to do. So that's what baselines the receiver sensitivity. Always you want a receiver which can actually detect the maximum, the lowest signal it can detect in the presence of noise. So that is how it is benchmarked. You need a receiver. So there are all specs compared to a standard saying your receiver has to meet this so that you can coexist in your noisy environment. Okay. So that is the thing that we'll skip this. I think these are all, I think, just some numbers. So that's what you have to understand. Lowest level sensitivity desired gives you higher range and higher coverage. You can do it in the presence of noise. And this is also phase noise, as we talked about in TX, right? As he said, there is a clock is not a single tone, it has a spread. So same thing, what happens is when you multiply with something which is having a non-ideal skirt, right? We said any multiplication just adds and subtracts frequency. It just adds and subtracts, right? So if something is residing in your nearby band, we saw that green curve, not the green, the green interference in the previous one. He'll take some part of the information and put it. There's a residual information. So you need the phase noise, right? Should be very good. Otherwise, it fold and give back that information. So that is also a problem. Just to understand, like, these are the key parameters, right? Now this is the dynamic range blocker, right? This I've talked in a different context. This is the signal. This is a jamming signal. Suppose somebody puts a jammer. It's not a physical jammer, but somebody else is transmitting, and that looks like a large information compared to this, right? Your receiver should not get saturated with this. Your receiver should be able to detect this, but it should have resolution to actually figure out what this information is. That's called dynamic range of a receiver. It's a range of suppose your receiver saturates right here. This is the level of the receiver. Receiver just saturates, clips. Then nothing you can figure out. Your clipping level of the receiver should be greater than what your blocker or a jammer needs to be, so that you are still able to represent this, but then you will have resolution to figure out what the signal is. This is called dynamic range, or what we call as, see, this is the the noise, right? And then this is the full scale. So usually the larger and larger you have, right, you can actually support larger and larger tolerance of blocker. So this is one of the key specs in any cellular communication, because many things coexist. So you need a good blocker tolerance. And this we already saw. The ADC rate is decided by the bandwidth. Like, minimum rate should be twice the bandwidth. So that's what decides the ADC rate. And ADC resolution, again, we saw, right? ADC resolution decides, I have not discussed what this means, but ADC resolution is more noise. If you are not able to represent, you are adding noise, that is this black level. If your ADC is lesser and lesser number of bits resolution, this black will keep going up. You need this to be, it should be able to detect very small level of signal, means you need higher and higher bit precision in the ADC. That's what it means. Okay. So this is what I think we looked at, right? We started with the signal. It went here, same thing. This signal went back to the top. It's just to show a summary of what this is, the legacy architecture that we had, and the things that where the impairments were. One, we saw the phase noise. We saw the non-linearity, which is calling the spectral leakage or flare up. You saw thermal noise, why need a low noise amplifier, and ADC I talked about. ADC bit resolution should be good, otherwise you are corrupting the information, you are not able to detect that information. So this sort of summarizes a typical a signal chain, right? So, and then as part of it, we also saw you need filters in different places, because before mixing you will have to filter out, otherwise the signal which is onto the other side of the clock frequency that you are trying to mix, right, comes in. So you need a filter, and then there is a challenge in a filter if the frequency is very small compared to your center frequency, all this. So this all has led to evolution of architectures when we move to two more new architectures that I am going to describe for 5G, right? We'll go back. Okay, before that, I think maybe a quick thing, right? We said what is a non-linearity, we talked about, right? So PA, so the power amplifier is the one which blasts signal. I said, right, linear curve. The curve is linear, but it just bends because it's getting saturated. This is what you can represent as square, cube. If you put it in an Excel curve, Excel sheet, and do a trend line fix, right, it will show some component of square, cube. So fundamentally it means like input to output is not linear, it's just bending. So what is done for it? So one thing definitely to note is it is on the transmitter chain, because you are sending the information, right? You are not receiving information, you are sending information. So what you can do, right? Let's say I have a opposite curve that I generate in the data that I send. Suppose I know, right, at 10 volts my signal is going down. I will not give 10 volts, I will give like 10.2 at that high frequency, so that after reduction, see, this is the curve that I am trying to send, and this is the curve that PA is trying to do. If you just multiply both, right, I will get a linear curve. It's like a pre-compensation. You can do a pre-compensation because it's what you are sending. You can scale the data and you send. That is called digital pre-distortion or digital pre-compensation. But this curve has to be fixed. right? If I have to know this curve has to be fixed so that I have to do the opposite of it. But typically things change, PA changes with temperature and stuff. So you can't do it just as one set condition. You have to keep doing it in the background. You have to keep constantly looking at some temperature changes. If it's day night, right, this curve will change, how much it bends. So you will have to keep changing this to compensate for it depending on what is changing in this, right? So that's where a feedback loop comes. This is what we saw in the first one. There is one more chain called observation or feedback receiver. It's very simple. It looks at the PA, you know how much it is curving. You put an ADC, you take the digital, but you know what I want to send, what I have received after this bending, right? I can get this information. You try to compensate and see what I need to compensate in the transfer function as a correction so that at the output it looks linear. So this is a digital pre-distortion. This is anyway a separate theory or a signal thing. I'm not going to do the details, just to introduce the third signal chain, like receive transmitter and a feedback signal chain. Okay, so now let's go into some evolution of standards, right? So definitely you see, right, as the mobile traffic over the years, right, the number of users has grown, right? You will have to support more and more people, right? Obviously one part is the standard evolution, like 4G to 5G. One of the things about 5G is it has to improve the capacity, like with the same tower I have to support more users, more dense users that that needs to come in. The other thing we saw as the thing evolved, right, I need more and more bandwidth, like Gbps, 100 Gbps compared to 10, which finally translates to some megahertz bandwidth in the signal. We saw that, right? What is the bandwidth? Mbps maps. So earlier 20 megahertz becomes 10 times. I'm just putting some example. It has to go to 800 megahertz, close to 1 gigahertz bandwidth here. The other thing, right, this I'll explain what this is. So this is like saying cell tower is sending this information to your mobile. There's something called multi-band. Like I said, right, Airtel gets one band in one frequency. You can send only that much of information. You can pack whatever you want. You do modulation, you pack that. But suppose I want to do double the information. What I can do, right, what I will do is, right, Airtel would also have got a band which is at a different frequencies. Let's say they got a 700 megahertz spectrum. So what they will do, right, they will send information split into two bands. The same mobile user will get one at 2.5, one they will get it at 700. The mobile should be capable of withdrawing both. It will merge both the information. So you are actually sending information through two channels. That is an easy way to increase bandwidth or data rate. You can send, like that's what the picture shows, right? You are sending two channels of data, meaning just to show visually there are two channels of data that is going in. The other thing that is very specific to 5G is number of antennas. We saw that, right? The first picture you saw a couple of antennas or 3 antennas, but in the last you saw the entire picture is like one 5G base station which looks like a box. So what is in it we will see. So it's basically the number of antennas have increased massively from 4G to 5G. So that is something called a massive MIMO or a multi-user beamforming. I'll just have one slide on it. I'll tell what that means. So effectively, right, the signal chain is the same, but you need more capacity, and the way it is done is there is a lot of antennas instead of one antenna. It's like a distributed antenna. We'll see what that means here. So instead of a single antenna, right, you have an array of antennas. That's how, right, that 5G box that you saw on the rightmost of the first picture is just like a box. Within that box, right, there are like say 64 antennas or 128 antennas. These are all small. I'm just representing as an antenna. What does that give if you have multiple antennas, right? So one thing you can do is, if let's say the information you are sending into each antenna, you try to change the amplitude and you send the delay. Right? You're sending the same information, but you try to tweak the delay and the amplitude. What you can do, right, you can sort of focus. So I think this is a general concept in many of the things like your ultrasound scanner or anything, right? It's like if you have multiple array of things and you send the same information but at different delays to each of them, the waves when they create, right, they actually constructively add because you are delaying, right? You can actually focus a beam in a particular direction by doing this. This is what 5G uses. It uses what is called beam forming. It forms a beam so that if you want to send information, right, one is you just blast information, right? You will interfere with the other guy. 5G, what it does, right, with this multiple antenna array, it can tune the beam to somebody sitting. If you are a mobile phone user, you're sitting on the 15th floor of a building compared to a tower, and you're on the bottom part of the or in a basement. The mobile tower can actually adjust and give a beam such that when you're on the top, right, it will send a beam which is focused there. When you're on the bottom, it will send a beam which is tuned to a different direction. The other thing it can do it, because you can focus the beam, right, you can actually make sure you're not interfering into a region of somebody else user which is there. So these are all the smart things that the 5G communication protocol does, which is enabled by a large number of antennas and beamforming, right. This inherently creates, you can send more information, you can increase the data rate, you can increase the capacity. This MIMO, right, what we call multiple input, multiple output beamforming, or they call it as active antenna system, because antenna is not passive now. You're trying to do this delay and stuff, which is also electronics behind it. This is the key heart of 5G, and that will move over to any technology that comes after this, like 5G or 6G, right. You can see in the picture, I can give a beam specific to a mobile user. That's how I am actually increasing the coverage, data rate, and all that stuff with the same hardware. And the hardware is the number of antennas have increased. So what is the, so if you see this, right, the goal or the push to is to get lower cost and higher bandwidth. So you can see on the left side, right, if you see, India is one of the actually the lowest cost for a mobile data. I think we don't like to pay, meaning we want 1 Gbps, we want 2 Gbps, 10 Gbps, but we don't want to get a increased bill or whatever in our thing, right. Compared to all other countries, right, India is the lowest, and maybe if you see, right, China is probably third. So this is where, right, what they want to do, right, they don't want to increase hardware, they want to do something where within the same hardware, right, they want to cover more number of users, they can't increase cost, right. So obviously there is push to increase number of users, which is channel capacity, but you have to reduce the cost per user, because nobody is going to willing to pay extra for the 10 Gbps that you want to give, right. And the other thing I said is the size of the antenna, the form factor of the antenna, and the other thing we normally don't worry about is the amount of power a base station takes, because it has to take power from there. With all this green energy and stuff, right, there is also push on newer technologies like 5G, right, should consume lesser power. So they will actually smartly figure out in the night time, let's say you have peak bandwidth during your office hours in a system, and in a night time, or let's say 1 o'clock in the night or 2 o'clock, right, people are all not going to use internet, right. It will smartly change the power, it will reduce the power that it wants to transmit, the number of antennas, right, we said it needs for all this beamforming, right, it will reduce the number of antennas it uses in night time. So all these technologies are built inside 5G, where it will smartly decide during the time of the day, depending on the bandwidth, how much should I use, how much power should I give. This is all saving the power grid or the energy from a power grid to make, they have to be certified as green. Right now, right, there are specs on how a base station, how much power the base station should consume, right. That's also there, which was not been there earlier, but the push of green energy and stuff, that is also coming into picture. So the 5G technology encompasses all this, like you can do beamforming, you can increase the coverage, you can do smart things to reduce or increase power. So that's what the fundamental thing, right, anything that we do as a semiconductor or a provider, right, we try to do innovations to provide lower power, higher channel count, reduce the size, increase the bandwidth, because data rates are going to increase as moving 4G to 5G. So that's the goal of what a semiconductor industry has to provide, so that the 5G or 6G, whatever is going to come in future, right, is getting enabled. So there are two quickly, right, I think we'll just go run through. We talked about there's a new, these two new architectures are specially used for 5G. I'm just coming to a 0IF architecture. So you can clearly say the signal chain is the same, just that, right, one filter went out from before the mixer, there was a filter, and there are two signal chains now, right. So each chain has become twice, and then one filter has moved. This is exactly like what I said, right, I said I and Q, you can do in phase and quadrature. So this RF PLL, right, one of the clock frequency is cos, one of the frequency is sine. So I said, right, we have to filter, otherwise both the informations will merge, otherwise you do cos and sine and then it shift on only one side. That's what this does. So the hardware is double, but it relaxes the filter, which is key in a system where you want smaller form factor. You can build all this in a semiconductor technology with very small size, but the filter size is decided by physics, so you can't do that. So the filter is removed, but you replicate it with two signal hardware chains, and how efficient you can do it in area and power, right, is the differentiation that you bring. You're removing the filter, making it smaller, but you're putting more signal chains. That's where innovation comes in circuit design or whatever process technology that you use, right, to double this chain. So that is 0IF. So now I'll come back to this is the recent trend that is driving 5G, which is called RF sampling transit. It's very simple. If you see the signal chain, many of the blocks have gone away. There is no mixer, completely gone away. Filter is also gone away. So it's directly what you are doing, right? You have an ADC converter which directly runs at gigahertz of speed, directly samples a signal. Everything you want to do, mixing and everything is done in digital. So the advantage that gives is, I said right, dual bands. I think I'll just go back to dual bands. You said right, somebody sends at 700 megahertz, somebody sends at 1.6. To do 700 megahertz, I have to do a full signal chain. To do a 2.5, I have to do a full signal chain that we saw. The entire thing has to be replicated. But if you do this, if you are able to cover with an ADC or a D2A, which can cover all the way till 3 gigahertz, you just do one hardware at the front. Your digital, right, can split all that information that it wants. So it enables reuse of hardware with a single hardware, reducing size. That's the biggest advantage that this brings in. It's called RF sampling. It means that your ADC and DACs are directly sampling at RF. They are not dealing with information after mixing. The mixing has gone out from analog into digital, and digital is just a question of what you do in your digital implementation. It's a DSP thing, right? You have removed it from here, and this also enables the way for software defined radio. That is, I think, some of the terms that you might come across when you look at, right? SDR is a software defined radio, because what they want to do, right? They want to employ the same radio for different, the Airtel, right? See, Airtel is actually not the guy who's doing the hardware. It's like Ericsson or Nokia are doing the hardware. So they are servicing different regions, right? I'll just go back to the this foil, right? So if you see this, these are the different countries and where the spectrum allocation for different countries. So you see, right, India, the 5G is mostly at a 3.3, 3.6 gigahertz is the carrier frequency band. And if you see Japan, you'll see somewhere around 4.5. US is also similarly in this band. And you can see somebody else, right, China is at 2.5. So for doing all this, right, you need those filters specific to the band, you need this PLL specific to the bands. But what does the RF sampling, the last architecture that enabled, if you're able to do everything together, the same hardware by software change, because DSP you can change, you can do a upgrade on a DSP software or a firmware, right? You don't need to change the hardware. Hardware means you have to change the filter. Physically you have to replace the filter. The same hardware can be used across regions, and they can do software configurations to it. That is the other reason why that RF sampling or whatever we saw the third architecture, right? Remove everything, push everything to digital, just do the bare minimum analog, take an ADC, take a DAC, sample the signal and give it to digital. Everything is done in digital. But the challenge in that is you need to have technologies to build those high speed ADC converters or DAC converters. That's where the challenge comes. Okay. So, so this I think is just two common modes of communication are there. One is FDD and TDD. I said, right, like transmit and receive, right, has to coexist. So there are two ways of doing it. One is you split the frequency, like the transmit frequency is slightly shifted, receive frequency is slightly shifted. You frequency duplex that when you are doing a communication, or you do it in time slots. That is like a TDD, where frequency is the same, but you give time slots. Let's say when some transmitter is transmitting, the other side should not transmit. So you need to synchronize. Like let's say I am transmitting in the phone, the guy who is receiving, right, will not transmit at that time. He will receive the information, then he knows when he has to transmit. At that time, I am not transmitting. So at least for the duplex information, that's like time to, you give slots, like saying this guy, the transmit and receive have slots of information where you want to send information. So this is the TDD, FDD. This some of the words. Usually all the 5G communication systems, right, are moving to TDD, not to FDD, because it's more complicated because of filtering and requirements, right? You have a nearband frequency, then your hardware needs to be changed. TDD gives that benefit, the frequency is the change. Same, you can do time slotting in your digital. So most or almost all of the 5G systems right now use time division duplex or TDD systems. And this is probably, I think, the last foil that I want to tell. What at TI, right, what we have been doing, right, over the years. This is just to show the evolution of what we did. Like 2017 is where I think the thing started, the 5G deployment probably in China, because India is still late, but China had already started like prototypes and stuff. So we did the first RF sampling transceiver, the third generation that we said, right, for 5G, we started with that. So we did that at that time to enable the 5G evolution or trends in China. Then over time, right, over the years, we have done multiple generations of products. You can see how it has evolved. Like this middle one, right, was supporting a smaller bandwidth, because the bandwidths all started with 200 megahertz at that time when 2013 is deployed. But that is what I think currently is getting used in India or deployment, because typically, right, compared to deployment and R&D, right, R&D always leads by 5 years. So whatever is getting employed now is probably the work of what was done 3 years before, where they have done an R&D. So you can see the evolution of frequency, like you moved from 200, now it is 600 megahertz. This is what they are asking for the next generation of TDD. We may not see it in India, but the deployment in China, right, they are looking for 600, which will come 2-3 years later. So you can clearly see, right, the RF sampling transceiver is one of the things that is taken over with the advantages that we discussed for whatever it is. The second one architecture is also there that I mentioned, zero IF architecture, which removes the bulky filter. So the first architecture which we discussed about, the legacy architecture, right, that is just to introduce, right, that typically is still there, but it is all on your macro like GSM, not the 5G, the 3G, the 4G, right, still use that, meaning that's the majority of the market, because there's so much effort and money that financial implications to change all the base stations. It will take, I think, 5-10 years, even though when you say 5G is coming here, 5G is not all base stations are not going to be 5G. So slowly it will evolve. I think as they upgrade the base station to the next gen, right, it will be 5G. But existing 3G or GSM is actually still widespread even in the entire world. Things will move. As we move on, right, things will move and 5G base stations will become the norm, and then 6G will be the ones that will start to take over maybe 10 years later. But it will take time to move. But the summary of all that I'm saying to that is there are a lot of things that you have to do in architecture to enable bandwidth, power, and you can see the evolution of the size, right. So this is, I think, the latest. It uses one of these parts. It was, I think, presented in the Mobile World Congress, right, where this Ericsson. So it's a base station done by Ericsson. It actually weighs only 19 kgs. So they have that as a benchmark. Typically the older ones, right, the base stations used to be like 40 kgs, 50 kgs, you can't carry. 19 kg is like typically one user can actually carry, and then you can just put it onto any fixture that you want, right. So it is evolved from wherever things were at 2017 to where we are in 2033. And then with things you can see, right, like India probably is lacking, China and Korea are well ahead, US is also actually lacking in deployment, Europe is also lacking in 5G deployment. The things, the regions which have predominantly deployed 5G are South Korea and China right now, and India is actually taking the step now, and similarly to US as well. And you can see, like, just to show, like, we have what all has to be enabled, like from a power consumption, the innovation, the architecture, and I hope, like, the signal chain, right, starting from the basics, why a particular thing, right, when we say weight, or why you move to this architecture, why RF sampling architecture is better, why 5G uses it, right. I believe, right, the kind of top level view that I have given, right, you are able to connect at a top level, meaning it's obviously there are a lot more details into it, but just at a top level, right, you can at least connect to why a particular architecture is chosen, what are all the different aspects of a communication chain which is deciding a particular architecture or a particular direction of evolution. I think that was the whole objective of this whatever presentation or talk. So I think probably I went overboard by 5 minutes. So if any questions you have, I think we can take. Yes.
Actually, sir, you have talked about the temperature dependence. So, sir, as in India, sir, temperature is increasing, sir, 50 degrees Celsius and above. So, sir, will it impact on the communication network?
Yeah. So so typically, right, when we do any of this board or whatever, like this equipment is done, right. So multiple things they take care. One is, right, obviously your ambient temperature, your external temperature is, let's say, changes from 10 degrees to 40. Take Rajasthan, right, it goes from 50 degrees to 10 degrees or whatever, or 50 degrees to 0 degrees, right. But typically, right, in a system, I said, right, power amplifier is the biggest power consumer or a power, because it has to blast so much of power. It's like 40 watts or 100 watts of power. One power amplifier has to blast 100 watts of power, the antenna that you have. in your base station is 100. That is the major 80% of your power is coming from that power antenna. So there are some cooling solutions that they have to do in a base station fundamentally. So even though your temperature is 25 degrees outside, the chip or the IC that sees, right, it will see 75 degrees temperature inside. So they have to do a cooling solution so that any variations in your ambient, the cooling solutions takes over. That is already done. And in addition to it, right, all the chips that we do or the board that they do, right, has to take a variation of temperature and meet all the performance that I said. Like they have specs, right, all of them to meet. So fundamentally, to answer the question, right, there are variations, but when you define a spec or a hardware design, right, it typically, right, at least for semiconductor, right, they always take minus 40 degrees. Your device has to work fully. It has to work at 125 degrees. That's what. So that covers for, this is not the change that you see in an external environment. That is because minus 40 to 125 is accounting for your ambient change plus the change in your board because of this power amplifier power is, like I said, night time your power amplifier can go down. So typically the range of design for a hardware is much higher than what you can see in an environment. So always it's minus 40, 115 or 125 is a usual thing that is taken for all semiconductor designs, ICs or boards that they have to meet that spec. Otherwise, they are not qualified to be used as a communication system.
Sir, one more question. Sir, as you said that to reduce the size of the antenna, we usually send higher frequency.
Yes.
So, sir, can we do the same, apply the same logic in the space communication thing? Sir, we usually see the large dishes there. So, can we like use the higher frequencies? Can they use the higher frequencies to reduce?
Yes, I think mostly, right, at least some of the things, right, see, satellite communications are all 8 gigahertz. I think there are something at 20 gigahertz also. So the only problem, right, some of the frequency bands, right, are already allocated for some special purposes. For example, right, satellite, they allocate already a frequency band. Most of the things, right, defense, I think you would have heard about radars, right? Radars are there everywhere, usually. So there are set bands of frequencies where people can't reintroduce a new communication system. It is all defined by defense or by the government or whatever, right? For example, let's say 25 gig or 26 gig, right, is used for some of the defense radars, even 20 gig. So 8 gig to 25 gig, right, you can't introduce any communication system. Meaning you can't decide, like somebody out of the blue, right, Airtel decides I want to send some information, right, they can't decide. Because those bands, right, are already done for a purpose, they don't want interference, right? These bands which are available in this 3 gig, right, they are all, that's why they were free and communication standard is getting defined. Some of the existing frequencies at higher frequencies we can't use as of now because they have to revamp the entire system. Defense system is golden, they don't want to change it, meaning they will change. So satellite also there is something at high frequency, but you can't do out of the blue, right, you can't decide like somebody comes and say, okay, I want to send something at a higher frequency. That's why, right, the spectrum is not free, in the sense it's free, they auction, and there are only specific bands you can buy, even region wise, right? That is very critical. And even if you see, right, there is a, you would have learned, I mean, you would have talked about this self-driving vehicles, right? So they have allocated a frequency where in a road, right, they have to talk. There are radars in there, they're called automotive radars. So to communicate it for self-driving vehicles, they have radars, small radars. Those are all running at 77 gigahertz. So the frequencies are set such that, right, for very critical applications, there is no desired interference that comes in. That standards are set. So out of the blue you can't go and do, but obviously there are some satellite bands which do operate at high frequency. One thing to note, right, higher frequency, one other disadvantage which I didn't talk about is the power. If you send something, right, the higher and higher frequency rate actually will attenuate to a larger extent. It goes, if you want a higher frequency rate, if you had a 10-meter range, if you increase the frequency rate, it will stop in 1 meter. You have to send more power. So satellite, you think about how long you have to send the power. So that's a trade-off. It's fine, you can reduce the size of antenna, but you can't realize the amount of PA power to send. So there's a trade-off. You have to send for long distance, right? That's, if you send very high frequency signal, right, it will not reach the level it will reach. So there's a trade-off. They have to evaluate what is bigger. Antenna will be smaller, but you can't design that power in a power amplifier to send. It will ask for some obscene amount of power you can't do. That's a trade-off always. Yeah. So any more